Today's customers have an increased awareness and commitment to quality and service. This places new demands on dealership technicians who are trying to achieve a high level of customer satisfaction. To assist the technicians in meeting this demand for service excellence, the Ford Parts and Service Division has introduced the Service Technician Specialty Training (STST) program. While developing this improved approach to service training, the technical training staff consulted with the training subcommittee of the National Service Managers Advisory Committee, as well as the District Service Engineers Advisory Committee. The result is a training program that will make available to Ford and Lincoln Mercury technicians the information and skills necessary to fix it right the first time. A full menu of new courses are being developed to fully train technicians in these specialty areas: engine performance, engine repair, suspension and steering, electrical systems, climate control, manual transmission and drivetrain, automatic transmission and drivetrain, brakes, and pre-delivery. Training schedules provided by your district office will announce when courses relating to these specialties will be offered.
This video training presentation is designed to highlight the features of the 4.6-liter modular engine manufactured by the Ford Motor Company. The 4.6-liter modular engine is unique because some components are designed to be interchangeable from one modular engine to another. Examples of this feature would be the pistons, valves, valve springs, and cam followers. They are designed so that the pistons used in the V8 modular engine also can be used in the V6 modular engine. The modular design not only eases the manufacturing process, but also increases the quality control of the parts. A point to note is that the 4.6-liter engine is not freewheeling. If the engine jumps timing, damage to the pistons and valve train can result. The 4.6-liter modular engine is a lightweight, high-horsepower engine. It is capable of producing 210 horsepower at 4,600 RPM, well above that of the 5.0-liter engine. The 4.6-liter engine is called a square engine due to the 90.2 millimeter bore and 90 millimeter stroke. The engine features a newly designed cast iron 90-degree V8 engine block. The engine block includes dedicated positions for accessory component mounting, such as the alternator, AC compressor, and power steering pump. This design eliminates the need for additional brackets and makes the engine more compact, lighter weight, and improves noise and vibration concerns. The crankshaft used in the 4.6-liter engine is made of a cast alloy iron for durability. It is cross-drilled for better oiling of the connecting rods and main bearings. The crankshaft also features rolled journal fillets that add strength and durability. The benefit from this crankshaft design is the ability for it to withstand higher RPMs. This lays the groundwork for improved engine performance and durability. The main bearings used on the 4.6-liter engine are made of aluminum and small in size. They are smaller than conventional main bearings due to the torque-to-yield fasteners used to secure the main bearing caps. These bolts are manufactured to aircraft quality standards, which basically means that the bolts are precision fasteners manufactured to very exacting tolerances in both material and size. Torque-to-yield fasteners are used on several components for the 4.6-liter engine. It is important to note that torque-to-yield fasteners are designed to be used one time only and must be replaced after they have been loosened or removed. These fasteners allow designers to get more work out of the bolt. Smaller size bolts can provide the same force as a larger size bolt because the size of the bolt will be more consistent. In reducing the size of the bolt needed, the size of the component it secures also can be reduced. The result is the ability to use a strong, durable, yet smaller and lighter weight bolt and component. This technology is a great advantage in the development of a powerful yet smaller and lighter weight engine. In the 4.6-liter engine, the thrust bearing and the number 5 main bearing is a one-piece design. The main bearing caps have been designed differently because of using torque to yield bolts. Like the main bearing caps are smaller in size and width and lighter than conventional main bearing caps. The main bearing caps are numbered and have an arrow on them that points to the front of the engine. This makes the assembly of the caps easier. Jack screws and side bolts are used to reduce the amount of distortion the main bearing caps and cylinder block encounter during assembly. Reducing cylinder block distortion allows for a more stable and evenly supported crankshaft. But the use of jack screws and side bolts require a special procedure for installation. The side bolts must be removed first. The jack screws are removed second. These screws have left-hand threads, and loosening requires turning them counterclockwise. The main bearing bolts are removed last. The torquing sequence is the reverse order to the detorque sequence. The main bearing bolts are tightened first. The jack screws are torqued second. Remember that these screws are left-hand threads. Tightening requires turning them clockwise. The side bolts are torqued last. These sequences are critical for proper crankshaft support. The pistons used in the 4.6-liter engine are of cast aluminum design with dished dome piston heads. They are small with a shorter skirt area than many other pistons. One compression ring, one compression and scraper ring, and one oil ring are used with these pistons. Each ring is designed differently and cannot be interchanged. The connecting rods used on the 4.6-liter engine are made of compressed iron powder. The connecting rods do not have an oil squirt hole to lubricate the piston pins and cylinder walls. Controlled oil leakage through the main and connecting rod bearings allow oil to be slung outward to cool and lubricate the piston heads and cylinder walls. The connecting rod design also uses a cracked rod bearing cap rather than a conventional machined bearing cap design. Basically, this design means that the connecting rod and bearing cap is formed as one piece. Then the bearing cap is cracked from the connecting rod. To do this correctly, scribe lines are etched on the inside of the bore, much like a scribe mark on a piece of glass. The connecting rod and bearing cap are then cracked into two parts. The result is a two-piece connecting rod that has rough surfaces that are an exact match. When the two pieces are fitted together, they will join perfectly and result in improved strength in the bearing area. Torque-to-yield bolts are used on the connecting rod bearing cap assemblies. Be sure to follow all shop manual procedures during assembly, and remember that the bolt must be replaced when loosened or removed. The cylinder heads used on the 4.6-liter engine are of a cast aluminum, overhead camshaft design. The unique feature of the cylinder heads are their ability to be interchanged with one another. It is important to note that although the cylinder heads are interchangeable, the camshafts are not. Basically, the only changes that would be necessary to switch the cylinder heads from one side to the other would be to switch timing chain tensioner locations and the camshafts. The tensioner oil feed hole plugs also must be relocated. The cylinder head gaskets are a steel core with laminated Teflon gasket surfaces. Unlike the cylinder head gaskets are not interchangeable. The 4.6-liter engine uses a single overhead camshaft design, which allows for better performance and durability of the engine. The camshaft lobes are narrow in width and have a high lift, long duration profile. Narrowing the width of the lobes decreases the weight of the camshaft. The high lift, long duration profile of the camshaft lobes causes improved volumetric efficiency characteristics for added performance. Another new feature of the 4.6-liter engine cylinder head is that the camshafts are held in place by camshaft cluster caps. These are two one-piece upper bearing assemblies that hold the camshaft in place and provide the upper bearing surface. The camshaft bearings are the machined surfaces of the cylinder head and cluster cap. If the bearing surface is damaged, the cylinder head and/or camshaft must be replaced. The proper order must be followed when removing the camshaft clusters. The torquing sequence is used to tighten the bolts. The proper sequence must be followed to prevent damage to the camshaft. Roller cam followers are used to convert the rotary motion of the camshaft to the up and down motion needed for valve operation. The cam followers are beveled at the point where the followers contact the valve. This bevel causes the valve to rotate as it operates. This rotational motion of the valve helps prevent carbon from building up on the valve seat for continued smooth engine operation. Hydraulic lash adjusters are used to ensure constant cam follower to valve contact. The hydraulic lash adjusters are similar to conventional hydraulic lifters and mount directly to the cylinder head. Note, hydraulic lash adjusters cannot be serviced and must be replaced. A 2-valve per cylinder configuration is used on the 4.6-liter engine. A large intake valve and a small exhaust valve allow for better volumetric efficiency. The valves are designed with a thin seat area for reduced weight. Note, care should be taken during engine service to prevent the valves from being damaged. The valve guide seals are a one-piece design that includes the spring seat. The assembly is fully seated into a recess in the cylinder head. This design prevents the spring seat from rotating during engine operation to maintain a more uniform valve spring tension at all times. Another feature of the cylinder head is the use of an oil orifice. The oil orifice is used to maintain sufficient oil pressure in the lubrication system and still provide oil for lubrication of the camshaft journals, cam followers, and timing chain tensioners. An oil reservoir area is built into the cylinder head and allows for a small amount of engine oil to be held in the cylinder head to lubricate the camshaft bearings and components during the initial startup and running of the engine. Timing of the engine is accomplished through the use of 2 timing chains, one for each camshaft, driven by sprockets on the crankshaft. The 2 separate crankshaft sprockets are mounted back-to-back at the front end of the crankshaft. Care should be taken to install these sprockets in their proper location. The timing chains and sprockets are marked with indicators for setting engine timing. Marks are stamped in the crankshaft and camshaft sprockets, and gold-colored chain links are located on the timing chains to make proper engine timing easier to identify. The 4.6-liter engine is not a freewheeling engine. Very close tolerances are maintained to allow for maximum performance. It is recommended that the crankshaft and camshaft never be rotated separately. Rotating the crankshaft or camshaft separately can result in engine damage. Timing chain tension is maintained by 2 hydraulic chain tensioners mounted on the cylinder heads. These tensioners are fed oil from the main oil galley and hydraulically keeps tension on the timing chains. The hydraulic chain tensioners incorporate a safety ratchet lock to prevent the tensioner from collapsing when oil pressure is not present, like when the engine is shut off. Should service of the timing chains or tensioners become necessary, the tensioners must be collapsed before installation. Refer to the shop manual for the procedures to bleed the hydraulic cylinders of the tensioners. Engine oil pressure for the 4.6-liter engine is provided by a G-rotor type positive displacement oil pump, similar to the type used on other engines like the 1.9-liter engine, and is mounted on the crankshaft. The oil pump uses an internally vented relief valve to maintain system oil pressure at 20 to 55 psi, depending on engine speed and oil viscosity. The cooling system used in the 4.6-liter engine is of a unique design. The water pump and cooling fan are driven by the accessory drive belt. A new feature of the cooling system is the pressurized radiator supply tank. Coolant levels are checked and filled at the radiator supply tank. The supply tank should not be opened while the coolant is hot. A newly designed intake manifold is used on the 4.6-liter engine. The evaporative casting process is used in the manufacturing of this manifold. This modern casting technique is used to help assure smooth runner surfaces for improved airflow and performance. The intake manifold is mounted to the cylinder heads on flat surfaces. The new mounting configuration relieves stress areas and the cylinder head movement that was common during intake manifold tightening on V-type engines. The runners of the intake manifold are a tune port design for a more even distribution of air to the cylinders for improved performance. The intake manifold also incorporates PCV channels on the intake manifold runners and the intake manifold gasket. These channels provide a path for gases from the PCV system to be metered into the intake of each cylinder for a more even air-fuel mixture. Both PCV channels are connected to the PCV valve by 2 hose connections, one from each runner, mounted on the back of the intake manifold. A mass airflow meter senses the airflow to the engine. This information is monitored by the EEC4 system to help it control fuel delivery accurately. The 4.6-liter engine is equipped with a multi-port sequential electronic fuel injection system. The fuel injectors used with this system feature a new deposit-resistant 4-hole design. This new design helps to reduce the deposits that can cause clogging on the tips of the injectors. The EGR system used on the 4.6-liter engine is the pressure feedback electronic type. The ignition system used on the 4.6-liter engine is the electronic distributorless ignition system. The water pump, cooling fan, and accessories on the 4.6-liter engine are driven by a single serpentine belt. A spring-loaded self-tensioner is used to maintain constant belt tension at all times. This tensioner eliminates the need for periodic maintenance regarding belt tension. The special tools needed to service the 4.6-liter engine are rear seal adapter, tool number T91P-6701-A, valve stem seal installer, tool number T91P-6571-A, valve spring compressor, tool number T91P-6563-A, cam positioning tool, tool number T91P-6256-A, and throttle body adjustment wrench, tool number T91P-9550-A. The 4.6-liter modular engine has been designed to offer many advantages. The use of interchangeable engine components, a reduction in engine size and weight, a high horsepower output rating, excellent fuel efficiency, a reduction in exhaust emissions, and improved durability. These advantages add up to an engine that meets today's automotive needs for service and customer satisfaction. Welcome to this 1991 new model technical training video presentation. It is designed to help you become more familiar with the product you're working on. This video will familiarize you with some of the servicing procedures that you may encounter on the 4.6-liter modular engine used in the 1991 Lincoln Town Car. The 4.6-liter modular engine has been developed to meet the specific needs of the Lincoln Town Car. It is a V8 engine with single overhead camshafts, electronic distributorless ignition system, and sequential electronic fuel injection. The engine features aluminum cylinder heads with 2 valves per cylinder, an aluminum intake manifold, and a cast iron cylinder block, all adding up to a very lightweight and powerful engine. The 4.6-liter engine is designed to be durable and problem-free. However, when service is needed, there are a few procedures you should be familiar with. The following procedures are designed to enhance the shop manual, not replace it. Always refer to the shop manual before beginning any repair work. The following procedures are necessary for removing the 4.6-liter modular engine from the vehicle. To begin removal of the engine, you must first disconnect the battery, remove the hood, drain the coolant, discharge the air conditioning system. First, loosen the cooling fan. Then remove the fan and the fan shroud, the radiator and radiator lower hose, and cap off the water pump outlet fitting. Now, remove the air inlet tube. Next, carefully relieve the fuel system pressure and disconnect the fuel lines. Caution: be sure to follow all procedures for fuel system pressure discharge as outlined in the shop manual. Now, remove the wiper arms, the weather strip seal, and the left upper cowl from the vehicle. Now remove the right upper cowl and remove the wiper module assembly. You are now ready to remove the 42-pin connector and transmission harness connector and position them out of the way. Disconnect the accelerator and speed control cables with a screwdriver or similar tool, and the throttle valve cable. Next, disconnect the electrical connector and vacuum hose from the purge solenoid, and the power supply from the power distribution box, starter relay, and ground. Now, disconnect the alternator harness from the fender apron and junction block. Disconnect the vacuum supply hose from the throttle body elbow vacuum port and the heater supply and return hoses. Now, remove the clips on the air conditioning compressor inlet and outlet hoses and disconnect them using the spring lock coupling disconnect tools T81P-19623-GL, G2, or equivalent. Remove the accessory drive belt and the body ground strap from the dash panel. Now, raise the vehicle on a hoist and drain the engine oil. Once the oil has been drained, disconnect the exhaust system from the left-hand and right-hand exhaust manifolds and support it with wire on the cross member. Remove the retaining nut from the transmission line bracket and remove 3 bolts and stud retaining the engine to transmission knee braces. Next, remove the starter. Disconnect the oil pressure sender and the EVO sensor. And then the 4 bolts retaining the power steering pump to the engine block. Note that 1 bolt cannot be removed from the pump and will remain on the pump, and wire the pump out of the way. Now remove the access cover from the engine block to gain access to the torque converter retaining nuts, and paint the torque converter to the flywheel to index the 2 during reassembly. Rotate the crankshaft until each of the 4 nuts are accessible, and remove the nuts. Remove the 6 bolts that retain the transmission to the engine. Note that 2 through bolts are on the left-hand engine insulator and 1 through bolt is on the right-hand engine insulator. You are now ready to lower the vehicle. Once the vehicle is down, support the transmission with the Rotunda 2-ton floor jack 077-00042 or equivalent. You're almost done. Remove the bolt retaining the right-hand engine insulator to the lower engine bracket and install the engine lifting brackets. Connect the engine lifting equipment to the lifting brackets and raise the engine slightly. Carefully separate the engine from the transmission and lift the engine out of the engine compartment. Now that the engine has been removed, you may now perform any necessary repairs. And that's it for the 4.6-liter engine removal features. Next, we will show you the procedures for proper installation. Begin by installing the engine guide pins to the engine. Now carefully lower the engine into the engine compartment and start the converter pilot into the flywheel. Align the paint marks on the flywheel and torque converter. Note, ensure that the studs in the torque converter align with the holes in the flywheel. Fully engage the engine to the transmission and lower it onto the insulators. You can now remove the engine lifting equipment, brackets, and the floor jack. Next, install the bolt retaining the right-hand engine insulator to frame. Raise the vehicle on the hoist. After removing the engine guide pins, install the 6 bolts that retain the engine to the transmission and tighten to spec. Install the engine insulator through bolts and tighten them to spec. It is important to note that 2 of the through bolts are required on the left-hand insulator and 1 through bolt is required on the right-hand insulator. Install the 4 torque converter retaining nuts and tighten to spec. Install the access cover. Now, position the power steering pump on the engine block and install the 4 retaining nuts. Tighten the bolts to spec. Connect the EVO sensor and the oil pressure sender. Install the starter. Position the engine to transmission braces and install the 3 bolts and 1 stud that retain the braces. Now tighten to specs. Next, position the transmission line bracket to the knee brace stud and install the retaining nut. Position the exhaust system to both exhaust manifolds and install the 4 nuts. Tighten the nuts to spec. Remove the wire retaining the exhaust system and be sure that the system clears the number 3 crossmember. Lower the vehicle. Connect the outlet and inlet hoses to the air conditioning compressor and connect the alternator harness to the fender apron and junction block. Now connect the heater supply and return hoses and connect the vacuum supply hose to the throttle body vacuum port. The power supply is now connected to the power distribution box, starter relay, and ground, and the electrical connector and vacuum hose to the purge solenoid. Connect, and if necessary, adjust the throttle valve cable. Connect the accelerator and speed control cables, and connect the transmission harness connector and 42-pin engine harness connector. Install the wiper module assembly. Install the right upper cowl and the left upper cowl onto the vehicle. Install the weather strip seal and wiper arms. Connect the fuel lines. Install the accessory drive belt. Next, install the radiator cooling fan and shroud and install the air inlet tube. Then, reconnect the battery. Now that the engine is in, fill the cooling system. Evacuate and recharge the air conditioning system. Fill the engine with clean engine oil. And you are ready to start the engine. Be sure to check for coolant, oil, and fuel leaks. You've just learned the procedures for removal and installation of the 4.6-liter engine. If any questions or problems should arise, consult your shop manual. The following are the procedures for in-vehicle removal and replacement of the timing chains on the 4.6-liter engine. Be sure to follow all steps carefully. If you have any questions about the proper procedure, always consult the shop manual. Caution: never rotate the camshafts or crankshaft with the timing chains removed. Failure to follow these directions will result in engine damage. To begin replacement of the timing chains, disconnect both battery cables. Next, remove the cooling fan and shroud. Remove the air inlet tube. Next, carefully relieve the fuel system pressure. And disconnect the fuel lines. Caution: be sure to follow all procedures for fuel system pressure discharge as outlined in the shop manual. Now remove the wiper arms, the weather strip seal, and the left upper cowl from the vehicle. Now remove the right upper cowl and remove the wiper module assembly. Release the belt tensioner and remove the accessory drive belt. Disconnect the ignition wires from the spark plugs. Caution: be sure to avoid pulling on the ignition wires themselves. Always remove the spark plug wires from the plugs by gripping the blocked end of the spark plug wire and turning. Disconnect the ignition wire brackets from the camshaft cover studs. And remove the 2 bolts retaining the ignition wire tray to the coil brackets. Next, remove the 2 bolts retaining the air conditioner high pressure line to the right-hand coil bracket. Disconnect the ignition coil, condensers, and the CID sensor. Remove the 3 nuts retaining the right-hand coil bracket to the front cover. And remove the nuts retaining the left-hand coil bracket to the front cover. Slide the ignition coil brackets and the ignition wire assembly off the mounting studs and remove them from the engine. Remove the water pump pulley. Disconnect the alternator harness from the junction block. Then, disconnect the purge solenoid electrical connector, the AC compressor electrical connector, and the HDR sensor. Now, remove the retaining bolt from the positive battery cable bracket located on the side of the right cylinder head. Disconnect the canister purge solenoid vent hose from the PCV valve and remove the PCV valve from the camshaft cover. Remove the 42-pin engine harness connector and the transmission harness connector. Raise the vehicle. Disconnect the oil sending unit and EVO sensor. And remove the bolts retaining the power steering pump to the engine block and cylinder front cover. Note, the front lower bolt on the power steering pump will not come all the way out. Now, wire the power steering pump out of the way. Next, remove the 4 bolts that retain the oil pan to the front cover. Remove the crankshaft damper retaining bolt and washer from the crankshaft. Install crankshaft damper remover T58P-6316-D or equivalent on the damper and pull the damper from the crankshaft. Now lower the vehicle. Remove the bolts and stud bolts that retain the right-hand camshaft cover to the cylinder head and remove the camshaft cover. Remove the bolts and stud bolts retaining the left-hand camshaft cover to the cylinder head and remove the camshaft cover. Remove the 7 stud bolts and 8 bolts retaining the front cover to the engine. Now, remove the front cover. Remove the HDR wheel. Rotate the engine so that number 1 piston is at top dead center. Install the cam positioning tools T91P-6256-A or equivalent on the flats of the camshafts as shown. This will prevent accidental rotation of the camshafts. Remove the 2 bolts retaining the right-hand tensioner to the cylinder head and remove the tensioner. Remove the right-hand tensioner arm. Remove the 2 bolts retaining the right-hand chain guide to the cylinder head and remove the chain guide. Remove the right-hand chain from the camshaft gear and remove the right-hand crankshaft gear and chain. Remove the 2 bolts retaining the left-hand tensioner to the cylinder head and remove the tensioner. Remove the 2 bolts retaining the left-hand chain guide to the cylinder head and remove the chain guide. Remove the left-hand chain from the camshaft gear and remove the left-hand crankshaft gear and chain. That completes the timing chain removal procedure. To begin installation of the timing chain, first inspect the friction material on the tensioner arms and chain guides. If worn or damaged, replace the tensioner. Also, remove and clean the oil pan and the oil pickup screen. Both crankshaft gears are identical. Install the left-hand timing chain on the crankshaft gear. Ensure that the copper link of the chain lines up with the timing mark on the crankshaft gear. And install the left-hand crankshaft gear with the tapered part of the gear facing away from the engine block. Install the left-hand timing chain on the camshaft gear. Ensure the copper end of this chain also lines up with the timing mark on the camshaft gear. When installing the right-hand crankshaft gear, check that the tapered part of the gear faces toward the engine block as shown. Now install the right-hand timing chain on the crankshaft gear, ensuring that the copper link of the chain lines up with the timing mark on the crankshaft gear. Install the right-hand timing chain on the camshaft gear and ensure that the copper link on this end is also lined up with the camshaft gear timing mark. Note, it is necessary to bleed down the timing chain tensioners prior to installation. Care must be taken when bleeding the tensioner down. Position the tensioner into a soft-jawed vise. Using a small pick or a similar tool, hold the ratchet lock mechanism away from the ratchet stem and slowly compress the tensioner plunger by rotating the vise handle. Once the tensioner plunger bottoms in the bore, continue to hold the ratchet lock mechanism and push down on the ratchet stem until it is flush with the tensioner face. While holding the ratchet stem flush to the tensioner face, release the ratchet lock mechanism and install a paper clip or similar tool in the tensioner body as shown. This locks it in the collapsed position. Note, the paper clip must not be removed until the timing chain, tensioner arm and timing chain guide are completely installed on the engine. Lubricate the tensioner arm contact surfaces with clean engine oil and install the right-hand and left-hand tensioner arms on their dowels. Be sure that the shoes of the tensioners are in the proper position as shown here. Install the right-hand and left-hand timing chain tensioners, securing each with 2 bolts. Torque the bolts to spec. Remember, do not remove the lock pins until the timing chain guides are installed. Install the right-hand and left-hand chain guides, securing each with 2 bolts. Tighten each bolt to spec. Now, remove the paper clips from the timing chain tensioners and check that the timing marks are aligned on each gear. Now, remove the cam positioning tools. Then, install the HDR wheel with the rear mark and the flange toward the engine. Inspect the front cover. Apply silicone gasket and sealant E3AZ-19562-A or equivalent in the location shown. Install the front cover on the engine. And install the 7 stud bolts and 8 bolts retaining the front cover to the engine. Tighten the bolts to specification. Now, apply a silicone gasket and sealer E3AZ-19562-A or equivalent where the front cover meets the cylinder head. And install the camshaft covers onto the cylinder heads. Install the bolts and stud bolts into the right camshaft cover and tighten to specification. Install the bolts and stud bolts into the left camshaft cover and tighten to specification. Raise the vehicle. Now, apply silicone gasket and sealant E3AZ-19562-A or equivalent to the keyway of the damper as shown. Position the damper on the crankshaft and ensure that the key and keyway are aligned. Now, install the crankshaft damper using the crankshaft sprocket and damper replacer tool T74P-6316-B or equivalent. Install the damper bolt and washer and tighten to specification. Now, install the 4 bolts retaining the oil pan to the front cover and tighten to specification. Next, position the power steering pump on the engine, install the 4 retaining bolts, and tighten to specification. Connect the EVO sensor and the oil pressure sending unit. Lower the vehicle. Connect the 42-pin connector and the transmission harness connector. Now, install the PCV valve in the right camshaft cover and connect the canister purge solenoid vent hose. Next, position the positive battery cable harness on the right-hand cylinder head. Install the bolt retaining the cable bracket to the cylinder head. Next, connect the purge solenoid electrical connector and the alternator harness to the junction block. Then connect the AC compressor clutch and HDR sensor. Install the water pump pulley and tighten the bolts to specification. Position the ignition coil brackets and ignition wire assembly onto the mounting studs. Install the 7 nuts retaining the coil brackets to the front cover and tighten to specification. Next, install the 2 bolts retaining the ignition wire tray to the coil bracket on the engine and tighten to specification. Connect both of the ignition coils, condensers, and the CID sensor. Position the air conditioner high pressure line on the right-hand coil bracket and install the bolt. Connect the ignition wires to the spark plugs. Be sure that the plug boots are fully seated and in the proper position as shown. Install the spark plug wire bracket onto the camshaft cover. Now, install the accessory drive belt. Install the wiper module assembly. Install the right upper cowl and the left upper cowl onto the vehicle. Install the weather strip seal and the wiper arms. Connect the fuel lines. Now, install the cooling fan and shroud. Install the air inlet tube. Next, connect the positive and negative battery cables and check fluid levels. Start the engine and check for leaks. This concludes this video presentation of timing chain replacement. Should any questions on procedures or specifications arise, please consult your shop manual. The following video presentation outlines the procedure for in-vehicle removal and installation of the cylinder head on the 4.6-liter engine. All steps of the procedure must be followed carefully. If you have questions about any part of the procedure, consult the shop manual. Begin the cylinder head removal by disconnecting both battery cables. Next, remove the cooling fan and shroud. Remove the air inlet tube. Next, carefully relieve the fuel system pressure and disconnect the fuel lines. Caution: be sure to follow all procedures for fuel system pressure discharge as outlined in the shop manual. Now remove the wiper arms, the weather strip seal, and the left upper cowl from the vehicle. Now remove the right upper cowl and remove the wiper module assembly. Release the belt tensioner and remove the accessory drive belt. Disconnect the ignition wires from the spark plugs. Caution: be sure to avoid pulling on the ignition wires themselves. Always remove the spark plug wires from the plugs by gripping the blocked end of the spark plug wire and turning. Disconnect the ignition wire brackets from the camshaft cover studs. And remove the 2 bolts retaining the ignition wire tray to the coil brackets. Next, remove the 2 bolts retaining the air conditioner high pressure line to the right-hand coil bracket. Disconnect the ignition coil, condensers, and the CID sensor. Remove the 3 nuts retaining the right-hand coil bracket to the front cover. And remove the nuts retaining the left-hand coil bracket to the front cover. Slide the ignition coil brackets and the ignition wire assembly off the mounting studs and remove them from the engine. Remove the water pump pulley. Disconnect the alternator harness from the junction block. Then, disconnect the purge solenoid electrical connector, the AC compressor electrical connector, and the HDR sensor. Now, remove the retaining bolt from the positive battery cable bracket located on the side of the right cylinder head. Disconnect the canister purge solenoid vent hose from the PCV valve and remove the PCV valve from the camshaft cover. Remove the 42-pin engine harness connector and the transmission harness connector. Raise the vehicle. Disconnect the oil sending unit and EVO sensor. and remove the bolts retaining the power steering pump to the engine block and cylinder front cover. Note, the front lower bolt on the power steering pump will not come all the way out. Now, wire the power steering pump out of the way. Next, remove the 4 bolts that retain the oil pan to the front cover. Remove the crankshaft damper retaining bolt and washer from the crankshaft. Install crankshaft damper remover T58P-6316-D or equivalent on the damper, and pull the damper from the crankshaft. Disconnect the exhaust pipes from the exhaust manifolds. Lower the exhaust system and wire it to the cross member. Remove the bolt retaining the starter wiring harness to the rear of the right cylinder head. Now, lower the vehicle. Disconnect the accelerator and speed control linkage using a screwdriver or a similar tool. Disconnect the throttle valve cable from the throttle body and the vacuum supply hose from the throttle body elbow vacuum port. Disconnect both HEGO sensors and the heater supply and return hoses. Remove the bolts and stud bolts that retain the right-hand camshaft cover to the cylinder head, and remove the camshaft cover. Remove the bolts and stud bolts retaining the left-hand camshaft cover to the cylinder head, and remove the camshaft cover. Remove the 7 stud bolts and 8 bolts retaining the front cover to the engine. Now, remove the front cover. Remove the HDR wheel. Rotate the crankshaft to the 270-degree position. Caution, only rotate the crankshaft in the clockwise direction. Note, this will ensure that all pistons are below the cylinder block deck. Remove the 2 bolts retaining the right-hand tensioner to the cylinder head and remove the tensioner. Remove the right-hand tensioner arm. Remove the 2 bolts retaining the right-hand chain guide to the cylinder head and remove the chain guide. Remove the right-hand chain from the camshaft gear and remove the right-hand crankshaft gear and chain. Remove the 2 bolts retaining the left-hand tensioner to the cylinder head and remove the tensioner. Remove the 2 bolts retaining the left-hand chain guide to the cylinder head and remove the chain guide. Remove the left-hand chain from the camshaft gear and remove the left-hand crankshaft gear and chain. Remove the 1 bolt that retains the alternator to the alternator brace on the intake manifold. The 2 bolts retaining the alternator to the engine block and the alternator. Disconnect the EGR tube from the right exhaust manifold. Remove the 2 bolts retaining the thermostat housing to the intake manifold. Detorque the 9 bolts retaining the intake manifold to the cylinder heads in the proper sequence shown, and remove the intake manifold. Remove the intake manifold gaskets. Now, remove the ground strap and 1 stud bolt retaining the heater return line to the right cylinder head. Detorque the 10 bolts that retain the right cylinder head to the engine block in the sequence shown and in 2 steps. The first step is to loosen each bolt, 1 complete turn in sequence. The second step is to loosen the bolts completely in the same sequence. Note, the lower rear bolt cannot be completely removed due to interference from the evaporator housing. Use a rubber band or similar item to hold the bolt away from the engine block as shown. Now remove the right cylinder head. Remove the dipstick tube from the cylinder head and engine block. Detorque the 10 bolts retaining the left-hand cylinder head to the engine block in the sequence shown in 2 steps. The first step is to loosen each bolt 1 turn in sequence. The second step is to loosen the bolts completely in the same sequence. Note, the lower rear bolt cannot be completely removed due to the interference from the brake vacuum booster. Use a rubber band or similar item to hold the bolt away from the engine block for removal. Remove the left cylinder head. This completes the section on cylinder head removal. Consult the shop manual for instructions should you have any questions about these procedures. To begin cylinder head installation, you must first ensure that the surfaces of the cylinder head, intake manifold, camshaft cover, and engine block sealing surfaces are clean and smooth. Note, check that the crankshaft keyway is still at the 270-degree position. Now position a new cylinder head gasket on the engine block. For the right and left cylinder heads, install the lower rear bolts into the cylinder head and retain them with rubber bands or similar items. Note, the cylinder head bolts are torque-to-yield fasteners and must never be reused. These fasteners require special procedures for torquing. Failure to follow these procedures can result in extensive engine damage. Position the right cylinder head onto the engine block dowels. Apply clean engine oil to all cylinder head bolt spot faces only. Note, do not lubricate the threads of the cylinder head bolts or bolt holes. Next, remove the rubber band from the lower rear bolt and install the remaining 8 cylinder head bolts. Hand tighten all of the bolts. Now, torque the right cylinder head bolts as follows. The first step is to torque each of the 10 bolts in the sequence shown to specification. The second step is to rotate the 10 bolts in sequence 90 degrees. The third step is to rotate the 10 bolts in sequence an additional 90 degrees. Now, position the left-hand cylinder head on the engine block dowels. Apply clean engine oil to all cylinder head bolt spot faces. Remove the rubber band from the lower rear bolt and install the 8 remaining cylinder head bolts. Hand tighten all of the bolts. Now, tighten the left cylinder head bolts as follows. The first step is to torque the 10 bolts in the sequence shown to specification. The second step is to rotate the 10 bolts in sequence 90 degrees as you have done with the right cylinder head. The third step is to rotate the bolts in sequence another 90 degrees. Next, position the heater return line bracket and ground strap on the cylinder head and install the 2 bolts. Now position the intake manifold gaskets on the cylinder heads and place the intake manifold on the cylinder heads. Install and torque the 9 bolts that retain the intake manifold in the sequence shown to specification. Position the thermostat housing, install the 2 retaining bolts, and tighten to specification. Position the alternator on the engine. Install the 2 retaining bolts and tighten to specification. Now, install the 1 bolt that retains the alternator to the alternator brace on the intake manifold and tighten to specification. Rotate the camshafts until the timing marks on the camshaft gears are 90 degrees from the camshaft cover mounting surface. Install the camshaft positioning tools T91P-6256-A onto the flats of the camshafts. This prevents the camshafts from rotating. Rotate the crankshaft clockwise to the 315 degree or the top dead center of the number 1 cylinder position. Caution, only rotate the crankshaft in the clockwise direction and only as far as top dead center. Both crankshaft gears are identical. Install the left-hand timing chain on the crankshaft gear. Ensure that the copper link of the chain lines up with the timing mark on the crankshaft gear. And install the left-hand crankshaft gear with the tapered part of the gear facing away from the engine block. Install the left-hand timing chain on the camshaft gear. Ensure the copper end of this chain also lines up with the timing mark on the camshaft gear. When installing the right-hand crankshaft gear, check that the tapered part of the gear faces toward the engine block as shown. Now install the right-hand timing chain on the crankshaft gear, ensuring that the copper link of the chain lines up with the timing mark on the crankshaft gear. Install the right-hand timing chain on the camshaft gear and ensure that the copper link on this end is also lined up with the camshaft gear timing mark. Note, it is necessary to bleed down the timing chain tensioners prior to installation. Care must be taken when bleeding the tensioner down. Position the tensioner into a soft-jawed vise. Using a small pick or a similar tool, hold the ratchet lock mechanism away from the ratchet stem and slowly compress the tensioner plunger by rotating the vise handle. Once the tensioner plunger bottoms in the bore, continue to hold the ratchet lock mechanism and push down on the ratchet stem until it is flush with the tensioner face. While holding the ratchet stem flush to the tensioner face, release the ratchet lock mechanism and install a paper clip or similar tool in the tensioner body as shown. This locks it in the collapsed position. Note, the paperclip must not be removed until the timing chain, tensioner, tensioner arm, and timing chain guide are completely installed on the engine. Lubricate the tensioner arm contact surfaces with clean engine oil and install the right hand and left hand tensioner arms on their dowels. Be sure that the shoes of the tensioners are in the proper position as shown here. Install the right hand and left hand timing chain tensioners, securing each with 2 bolts. Torque the bolts to spec. Remember, do not remove the lock pins until the timing chain guides are installed. Install the right hand and left hand chain guides, securing each with 2 bolts. Tighten each bolt to spec. Now, remove the paper clips from the timing chain tensioners and check that the timing marks are aligned on each gear. Now, remove the cam positioning tools. Then, install the HDR wheel with the rear mark and the flange toward the engine. Inspect the front cover. Apply silicone gasket and sealant E3AZ-19562-A or equivalent in the location shown. Install the front cover on the engine. And install the 7 stud bolts and 8 bolts retaining the front cover to the engine. Tighten the bolts to specification. Next, connect the heater supply and return hoses, both HEGO sensors, and the vacuum hose to the throttle body elbow vacuum port. Now, connect the throttle valve cable. Next, connect the accelerator and speed control cables to the throttle body. Now, apply silicone gasket and sealer E3AZ-19562-A or equivalent where the front cover meets the cylinder head, and install the camshaft covers onto the cylinder heads. Install the bolts and stud bolts into the right camshaft cover and tighten to specification. Install the bolts and stud bolts into the left camshaft cover and tighten to specification. Raise the vehicle. Position the starter wiring harness to the right cylinder head and install the retaining bolt. Remove the wire retaining the exhaust system and make sure that the system clears the number 3 cross member. Position the exhaust system to both exhaust manifolds. Install the 4 nuts and tighten to specification. Connect the EGR tube to the right exhaust manifold and tighten the line nut to specification. Now, apply silicone gasket and sealant E3AZ-19562-A or equivalent to the keyway of the damper as shown. Position the damper on the crankshaft and ensure that the key and keyway are aligned. Now, install the crankshaft damper using the crankshaft sprocket and damper replacer tool T74P-6316-B or equivalent. Install the damper bolt and washer and tighten to specification. Now, install the 4 bolts retaining the oil pan to the front cover and tighten to specification. Next, position the power steering pump on the engine, install the 4 retaining bolts, and tighten to specification. Connect the EVO sensor and the oil pressure sending unit. Lower the vehicle. Connect the 42-pin connector and the transmission harness connector. Now, install the PCV valve in the right camshaft cover and connect the canister purge solenoid vent hose. Next, position the positive battery cable harness on the right-hand cylinder head. Install the bolt retaining the cable bracket to the cylinder head. Next, connect the purge solenoid electrical connector and the alternator harness to the junction block. Then connect the AC compressor clutch and HDR sensor. Install the water pump pulley and tighten the bolts to specification. Position the ignition coil brackets and ignition wire assembly onto the mounting studs. Install the 7 nuts retaining the coil brackets to the front cover and tighten to specification. Next, install the 2 bolts retaining the ignition wire tray to the coil bracket on the engine and tighten to specification. Connect both of the ignition coils, condensers, and the CID sensor. Position the air conditioner high pressure line on the right-hand coil bracket and install the bolt. Connect the ignition wires to the spark plugs. Be sure that the plug boots are fully seated and in the proper position as shown. Install the spark plug wire bracket onto the camshaft cover. Now, Install the accessory drive belt. Install the wiper module assembly. Install the right upper cowl and the left upper cowl onto the vehicle. Install the weather strip seal and the wiper arms. Connect the fuel lines. Now, install the cooling fan and shroud and fill the cooling system. Install the air inlet tube. Next, connect the positive and negative battery cables and check all fluid levels. Start the engine and check for leaks. This concludes this video presentation of in-the-vehicle cylinder head removal and installation. Should any questions on procedures or specifications arise, please consult your shop manual. This video presentation is designed to demonstrate the proper procedures for crankshaft and main bearing cap removal and installation. Be sure to follow all procedures carefully. If any questions should arise, consult your shop manual. Begin the main cap removal procedure by removing the side bolts from the main caps in sequence. The jack screws are removed second. These screws have left-hand threads, and loosening them requires turning them counterclockwise. Begin detorquing the main bearing caps in the sequence shown. Now remove the main bearing caps and the crankshaft. Remove the upper bearing shells. Before assembling the cylinder block components, all surfaces must be clean and free of chips, dirt, paint, and foreign material. Also, make sure that all coolant and oil passages are clear. Begin installation of the main bearings by installing the upper bearings into the cylinder block. Be sure to lubricate the bearings with clean engine oil. Now, carefully install the crankshaft. Check to make sure it rotates freely. Then, install the upper main bearing shells into the main bearing caps and lubricate the bearing surface. Next, install the main bearing caps and tap the caps down with a plastic hammer to seat them properly. Push the crankshaft forward using a screwdriver or similar tool to seat the thrust bearing. Note, remember that the main bearing cap bolts are torque to yield fasteners and cannot be reused. You must always replace the main bearing bolts whenever the main caps are removed. Now, tighten the new main bearing bolts in 2 steps. First, tighten the bolts in the sequence shown to specification. Next, rotate each bolt in sequence another 90 degrees and rotate the crank to check for binding. Once the main caps are installed and torqued, you are now ready to adjust the jack screws. The jack screws are tightened in 2 steps. Remember, these screws have left-hand threads, and tightening them requires turning them clockwise. First, torque each jack screw in the sequence shown to specification. Second, torque each screw 1 additional time to the second spec. Now, install the side bolts into the jack screws and tighten the side bolts in 2 steps. First, tighten the side bolts in the sequence shown to specification. Now, torque the bolts once more to the specification and in the same sequence. And finally, check the crankshaft end play in both directions as shown. You have just learned the procedures for removal and installation of the main bearings. If any questions or problems should arise, consult your shop manual. This video presentation will demonstrate the procedures to service the cylinder head of the 4.6-liter engine. These procedures are available in the shop manual. Note, the 4.6-liter engine is designed with strict tolerances. Be sure to follow all procedures carefully. Failure to do so can result in engine damage. The camshaft lobe must be at base circle before placing the cylinder head on the bench. This allows most of the valves to be in the closed position. This should be verified visually. Lay a cloth down on the bench to protect the sealing surface of the cylinder head during service. And carefully set the cylinder head down on the bench. Install the valve spring compressor tool number T91P-6565-A under the camshaft and on top of the valve spring retainer. Insert the 1 millimeter thick shim in between the top coil of the valve spring and compress the valve spring just far enough to remove the roller follower. Failure to install the shim will result in overcompression of the spring, and damage to the valve stem seal will result. Repeat these steps to remove the remaining roller followers. Next, remove the hydraulic lash adjusters. Then, compress the valve spring further and remove the valve keepers, the valve spring retainer, and the valve springs. Next, remove the valve stem seals using pliers and remove the valves. The next step is to remove the camshaft cap cluster assemblies. To remove the camshaft cap cluster assemblies, first detorque each bolt one turn in the sequence shown. Then remove each of the bolts in the same sequence. And remove the camshaft cap cluster assemblies by rocking or wiggling the caps while pulling on them. The camshaft can now be removed. To begin cylinder head assembly, position the camshaft on the cylinder head. Install the camshaft cap clusters. Hand start the bolts and tighten them down. Now, torque the camshaft cap cluster bolts in sequence to specification. Next, loosen the camshaft cap cluster retaining bolts in sequence, approximately 2 turns or until the bolt heads are free. Then, retorque all of the bolts in sequence to specification. Now, install the valves into the cylinder head. Note, a knotted rag or similar item must be positioned under the valve to hold it in the closed position. Install new valve stem seals using valve stem seal installer T91P-6571-A and valve spring compressor T91P-6565-A. First, position the valve stem seal. Then, place the valve stem seal installer on the seal. Now, use the valve seal installer T91P-6571-A to seat the seal into the cylinder head. Be sure to inspect the seal for proper placement before continuing. Now, position the valve spring and retainer onto the valves. Insert the 1 mm thick shim in between the top coil of the valve spring. Install the valve spring compressor T91P-6565-A or equivalent under the camshaft and on top of the valve spring retainer, and compress the valve spring far enough to install the valve keepers. Always remember to remove the 1 mm shim. Failure to install the shim will result in overcompression of the spring, and damage to the valve stem seal will result. Repeat these procedures until all valves are installed. Lubricate the hydraulic lash adjusters and install them into the cylinder head. Once the valves are installed, compress the valve spring using the valve spring compressor and shim, just far enough to install the roller followers. Repeat this step for each valve. This completes the cylinder head disassembly and assembly procedures. If any questions should arise, please consult your shop manual.
This video presentation will introduce the concepts that apply to threaded fasteners and the damage that can occur by not dealing with them properly. The bolt is certainly not a new device. It has been around longer than the car, yet it can be one of the least understood and most important parts on a vehicle. Extensive research goes into the study and designing of fasteners. Ford Motor Company uses a wide range of test equipment to ensure the fasteners can do their job right. Several factors affect the way a bolt holds a component together. The first step is to understand how a bolt works. As a bolt is tightened, the exposed threads stretch and the bolt becomes longer. The more it is tightened, the further it stretches. This stretching allows the bolt to remain tight when exposed to elements like temperature change and vibration. Proper tightening causes the bolt to stretch like a spring and then return to its original length when loosened. Over-tightening the bolt will cause it to weaken or break. Excessive tightening causes the bolt to stretch permanently and neck down in the threaded length. The reason for tightening bolts is to provide clamping force. Clamping force is the amount of pressure applied by a tightened bolt. A properly tightened bolt provides the best clamping force or load possible. Over or under tightening reduces the amount of clamping force the bolt provides. Bolt stretch is one feature of the bolting process. Surface compression is another. As load increases, the bolt and surfaces act like springs. The bolt spring stretches, and the surface spring compresses. How well the surfaces join becomes very critical when exposed to conditions like changes in temperature, vibration, and the type of gasket material used. Using multiple bolts to clamp two surfaces together makes proper clamping force hard to obtain. During tightening, the surface springs cause the tension of one bolt to affect the tension of the other bolts. How even the load is distributed between the bolts affects the durability and quality of the joint. Three other factors that affect clamping force are fastener precision, cleanliness, and lubrication. These conditions must be controlled for a durable joint. Fastener precision is determined by the material used in manufacturing, the quality of the threads, and the amount of variation allowed between the bolts. The closer these factors are controlled, the higher the quality. Thread and surface cleanliness during assembly is critical. The threads of a fastener must be clean for proper tightening. Dirt on the threads adds friction or resistance to tightening. This reduces the amount of clamping force the bolt delivers because friction uses up some twisting force. The bolt threads are cleaned using a wire brush. The threads of the bolt hole are cleaned using a tap. After using a tap to clean a threaded hole, be sure to clean any metal chips and dirt out of the hole. Failure to do so defeats the purpose of cleaning the threads. As a rule, feeling resistance while hand tightening a bolt means the threads need cleaning. The surfaces being clamped together need to be clean and smooth. Any dirt and old gasket material must be removed from the surfaces before assembly. The metal gaskets used on the 4.6-liter engine require that a special method be used for gasket removal. Do not scrape the cylinder head or engine block surfaces. On other engines, be careful not to scratch or gouge the surfaces when scraping away old gasket material, especially if the surface is aluminum. Dirt and old gasket material will lessen the clamping force being applied to the new gasket. Having to compress the dirt or old gasket material uses up some clamping force. This reduces the force available for sealing. Thread lubrication allows for proper bolt tightening. Apply a light film of engine oil to the underhead and threads of the bolt, not the bolt hole. This reduces friction during tightening. Some applications do not use oil on the bolt threads. An adhesive or lubricant may be required, or the threads may need to be dry. Always consult the shop manual and use what is specified. Bolts differ in strength, size, and thread. These differences determine the bolt a certain component requires. Only use Ford replacement bolts. Being able to identify bolts takes the guesswork out of selecting which one to use as a replacement. Using the wrong bolt can cause a failed component, repeat service, and a safety hazard. A bolt that is weaker than required will distort, loosen, or break under stress. Bolts are identified by length, strength, and the type of thread used. Identifying these areas will ensure using the proper bolt as a replacement. Bolt length refers to two areas, the overall length and the length of the threaded portion. The overall length measures from the bottom of the bolt head to the end of the threads. Thread length is measured from where the threads begin on the shank to the end of the bolt. Both of these lengths must be considered when selecting a replacement bolt. The strength of a bolt varies with the materials and heat treatment process used in manufacturing. Tensile strength is the rating given to the steel used to manufacture the bolts. A test machine pulls on a steel rod until it breaks. The tensile strength is how much force the machine used to break it. A system of grading allows the bolt strength to be identified. The Society of Automotive Engineers grades U.S. standard bolts on a scale of 1 to 8. Grade 1 being the weakest and grade 8 being the strongest. To identify the grade of a bolt, count the number of lines or marks on the bolt head and add 2. The bolt shown has 3 lines stamped in the head, indicating it is a grade 5 bolt. Hex nuts are graded in the same fashion. The number of lines or marks stamped into the surface indicates the grade. Always make sure the grades of the nut and bolt match. Metric fasteners are rated in a manner similar to U.S. standard bolts. Instead of lines or marks, they have numbers stamped on them in a common range from 4.6 to 10.9. The higher the number, the stronger the fastener. The threads on the bolt can either be coarse or fine. Coarse threads are farther apart than fine threads. Threads are identified by measuring the outside diameter and thread pitch. The outside diameter is measured using a micrometer across the high points of the threads. The actual measurement is usually less than the given thread size. How much less depends on the tolerance allowed in manufacturing. Measuring thread pitch requires using a thread pitch gauge or a steel rule. The thread pitch gauge requires matching the proper gauge to the thread pattern. This is the easiest method of measuring thread pitch. The steel rule method involves counting the number of threads per inch for U.S. standard bolts or measuring the distance between the threads for metric bolts. This method makes it hard to be accurate. Most bolts used in automotive engines are designed for a specific application. These bolts can vary in shank size, head size, thread pattern, and use an integral washer. Never replace these bolts with standard bolts. The features of the special purpose fastener allow it to meet the needs of a specific application. These bolts may not have a grade stamped in the head like standard bolts. Some specialized bolts must meet more rigid quality standards. More attention is paid to the methods used in manufacturing, the amount of control during manufacturing, and the selection of the materials. Less tolerance in manufacturing means the bolts will be more uniform in size than standard bolts. Particular attention is paid to features affecting the fastener's strength. Bolts have many uses, and certain devices help them apply the right clamping force. Improper use of these devices can result in the bolt breaking. When the application requires the bolt to penetrate the clamping surfaces, a hex nut works with the bolt. Remember, the grades of the nut and bolt must match. Again, bolt stretch and surface compression during tightening results in clamping force. The threads of the nut stretch with the bolt threads. Flat washers distribute the bolt load over a larger surface area. Be aware that flat washers have round and sharp-edged sides to them. The rounded side must face the bolt head. Installing a flat washer wrong causes the edge of the washer to gouge the bolt head, creating a weak spot. Under stress, this weak spot can cause the bolt head to break off. Mechanical locking devices prevent the nut or bolt from coming loose. These devices help in areas where varying loads and vibration are common. Cotter pins, locking tabs, and safety wire keep nuts and bolts from coming loose by preventing them from turning. Lock washers keep the nut or bolt from coming loose by applying tension to it. The added tension keeps the thread stretched when the stress on the bolt changes. Lock washers should be replaced after one use. Lock nuts cause a physical binding in the threads to prevent the bolt from loosening. After selecting the right fastener, an understanding of how to tighten them becomes very important. Tightening a bolt requires the use of torque. Torque is the twisting force applied to the bolt during tightening. Measuring torque allows for control over the tightness of the bolt. Then the bolt can provide the right amount of clamping force. To measure torque accurately, certain areas need to be considered first. How much the bolt stretches and surfaces compress become critical during torquing. These materials must remain within their elastic limit. Elastic limit refers to the maximum a material can stretch and still return to its original shape or length. Passing the elastic limit causes the material to retain some distortion or permanently increase in length. With fasteners, the idea is to get close to the elastic limit of the bolt. This provides the most clamping force possible. Excessive tightening will damage the fastener, and less tightening will not provide ideal clamping force. Friction is the major factor in torque measurement. Torque is the energy applied to the bolt, and friction uses up most of this energy. Reducing friction puts more of the energy into the tension of the bolt. A light film of engine oil on the bolt head and threads greatly reduces friction. Note, bolt threads should only be oiled when specified to do so. Consistent tightening and a stronger joint will result from this practice. The concepts of torque become more complex when multiple fasteners clamp two surfaces together. During tightening, each bolt affects the force applied by the other bolts. Even when tightened properly, the clamping force from the bolts can vary up to 50%. Surface movement, surface quality, gasket compression, friction, and dirt affect how well the load is distributed between the bolts. Improper torquing or tightening by feel can complicate matters even more. The result is usually a poor seal, a damaged component, or both. The cylinder head can be damaged by improper torque procedures. How the head bolts are loosened and tightened affects the shape of the cylinder head. A distorted cylinder head will not seal properly. Machining the cylinder head may repair the problem, depending on how much it is deformed. Overhead camshaft towers can come out of alignment by ignoring disassembly and assembly procedures. This leads to rapid camshaft bearing wear or damage to the camshaft. Unlike warpage, this type of damage cannot be repaired. To correct this problem, the cylinder head needs to be replaced. Main bearing cap disassembly and assembly is critical to crankshaft and engine block durability. Before removal, main bearing caps must be marked to ensure they are installed in the same place. These caps distort during assembly, and control is needed to limit this action. The engine block main bearings and cylinder bores can become misaligned from improper main bearing cap disassembly and assembly. The 4.6-liter engine uses jack screws and side bolts to keep the main bearing cap distortion to a minimum. While tightening the main bearing caps, a certain amount of distortion occurs. Tightening the jack screws and side bolts bring them back to their normal position. Specific procedures must be followed during disassembly and assembly of the main bearing caps, or engine damage will result. The intake manifold on V-type engines causes concerns during assembly and disassembly. During assembly, the mounting surfaces form a wedge that push the cylinder heads outward. This action can distort the cylinder head and cylinder bores. It should be easy to see the importance of following the proper procedures for disassembly and assembly. Many problems can be avoided this way. Two surfaces that are clamped together are under tension. Loosening the bolts allows the surfaces to relax. Distortion occurs when the surfaces relax unevenly. Before disassembly, make sure the components are cool. Heat causes the tension of the surfaces to be greater and harder to control. Loosen the bolts using a detorque sequence. This sequence allows the surfaces to relax at an even rate. Consult the shop manual before disassembly. It may specify a certain detorque sequence. If not, reverse the tightening sequence order. Then break the bolts loose in the detorque sequence. Note, do not use a torque wrench for detorque, or damage to the wrench may result. The torque wrench is the tool used for tightening bolts accurately. This wrench is a gauge that measures twisting force. The torque wrench allows each bolt to be tightened the same amount. This allows for better load distribution between the bolts. Torque specifications allow the bolts to be tightened the right amount. Extensive research determines these specifications, so the bolt applies the right amount of force for the component. An impact wrench should never be used for detorquing or torquing engine bolts. This type of wrench does not allow enough control over the amount and type of torque it delivers. An impact wrench delivers a hammer-like motion to tighten bolts. Proper even torquing cannot be obtained. The torque wrench can be controlled much better. The torque wrench is a precision measuring tool, much like a micrometer. These tools must be treated accordingly and never used as a rough service tool like a pry bar, hammer, or for detorquing bolts. Like any measuring tool, the accuracy of the torque value requires using the torque wrench properly. Proper gripping of the tool and the motion used are important. The torque wrench should be pulled at a moderate, even speed until reaching the specified torque value. Pulling too fast results in lack of control and poor accuracy. Pulling too slow causes the wrench to stop and start again. Stopping the torque wrench motion during tightening affects the accuracy of the measurement. The amount of force needed to start the wrench moving again is high. If the wrench stops, back the bolt off slightly and then continue. This allows for an accurate measurement. Multiple bolt applications require the use of a torque sequence. This is the order for tightening the bolts. Torque sequences allow the surfaces being clamped to move and settle as they tighten. Using the wrong torque sequence can result in a warped or distorted component. Multiple fastener applications also need to have the torque applied in steps. Usually 3 steps are used. Each step tightens the bolts more until reaching the torque specification. Each of these steps must be performed in the specified torque sequence. Torquing the bolts in steps allow the surfaces and gasket to flatten out evenly and provides a better seal. Refer to the shop manual for torque specifications, detorque sequence, torque sequence, and step divisions. If no step specifications are given, divide the torque specification into 3 stages. Torque to yield fasteners require a different tightening method. When a bolt stretches within the elastic limit, it will return to its original size. Stretching the bolt just past the elastic limit allows it to provide maximum clamping force, but will not return to the length it was originally. The area just past the elastic limit is called the yield point. This is where torque to yield fasteners are tightened to. Gasket compression, dirt, friction, torque wrench calibration, and surface quality are factors that reduce the accuracy of torque measurement. The torque to yield method overcomes these factors because each bolt provides the same load. In addition to a torque specification, torque to yield bolts are tightened a specified number of degrees. A 90-degree specification means the bolt must be tightened 1/4 turn. The reason this method is possible is that torque to yield bolts are precision fasteners. Turning the bolts the same amount allows them to stretch equally. This places the bolts in yield and allows the bolt loads to be consistent. Torque to yield fasteners allow smaller bolts to do the same work that larger bolts used to do. The use of smaller bolts allows for smaller component size and weight. This helps in the design of lighter engines. Torque to yield bolts must be replaced after one use. They are tightened past their elastic limit and will not provide proper clamping force when tightened a second time. The method for tightening torque-to-yield bolts is similar to the torque wrench method. The bolts are tightened in 2 or 3 steps in a specific torque sequence. An example of the torque-to-yield method is the cylinder head bolts on the 4.6-liter engine. A torque wrench is used for the first step of this method. The bolts are tightened to specification in sequence. The last 2 steps are performed without the torque wrench. The second step requires rotating the bolts 90 degrees in sequence. The last step requires tightening the bolts an additional 90 degrees in sequence. It is normal for the wrench to feel mushy or soft near the end of the second 90-degree rotation. Unlike the torque wrench method, if the wrench stops during torque to yield, it does not affect the tightness of the bolts. The 4.6-liter engine also uses these bolts for the connecting rod and main bearing caps. In hard-to-reach areas, the use of scribe lines helps to ensure the right amount of bolt rotation. After the first torque step, scribe lines on the surface at the 0, 90, and 180-degree points. Scribe a line on the bolt head even with the 0-degree line. The second step now requires aligning the bolt head and the 90-degree lines. The third step requires aligning the bolt head and 180-degree lines. This concludes the video presentation on fastening devices. If you have any questions, consult the video reference book or the shop manual before detorquing or torquing bolts.